Hey everyone, and welcome to This Explainer. Today, we are going to do something absolutely incredible. We're going to unlock one of the most famous foundational concepts in all of mathematics, Fermat's little theorem. But, and here is the best part, we are going to do it without getting totally bogged down in dense, confusing algebra. Instead, we're going to use a brilliantly simple visual metaphor. Basically, we're going to build some colored necklaces. By the end of this explainer, you'll see exactly how a tangible, physical story perfectly proves a really abstract mathematical truth.
All right, let's dive right in. Take a look at this. This is our big mystery for today. It's the formal definition of Fermat's little theorem. It states that if you let p be a prime number, for any whole number a to the power of p is congruent to a modulo p. Or another way to look at it is that p perfectly divides a to the power of p minus a. Now, I will be the first to admit this pure algebra, it looks highly intimidating at first glance. If you aren't fluent in modular arithmetic, your eyes might just completely glaze over. But honestly, don't worry. We are going to completely demystify this whole thing.
So, before we start actually drawing out these necklaces, we really need to frame our investigation. The central puzzle we're trying to solve here is this. Why does a prime number p have such a special structural relationship with powers like a to the power of p? I mean, what is it about prime numbers specifically that makes this division work out perfectly every single time? To answer that, we're going to have to step out of the realm of abstract symbols and step into the physical world.
Okay, let's move into section 1, colored necklaces and building the metaphor. What's really super cool here is how we can translate our daunting math variables into actual tangible objects. In our theorem, we had the letters p and a. Well, we are going to define p as the number of bead positions on a physical necklace, and we're going to define a as the number of possible paint colors we have available to color each of those beads. Suddenly, a to the power of p isn't just some abstract algebraic term anymore, it's a literal physical combination. Let's actually zoom in on this beautiful, vibrant necklace illustration here. Count the beads with me. 1, 2, 3, 4, 5. In this specific example we've drawn out, our prime number p is 5. We have exactly 5 bead positions arranged in a circle. Every single time we talk about building arrangements today, I want you to picture this exact circular structure in your head. Now, imagine we're building a massive pile of these necklaces. Let's call it pile 1. This pile contains every single possible color combination we can possibly make. So how do we calculate the total number of necklaces in pile 1? Well, if we stick to our example where our prime number p is 5 beads, and let's say we choose an A of 2 possible colors, let's say just red and blue. Every single one of those 5 beads has 2 color choices, right? So the total number of colored arrangements is 2 times 2 times 2 times 2 times 2. That is 2 to the power of 5, which equals 32. More generally, with p bead positions and a possible colors, the total number of arrangements is always going to be a to the power of p. Okay, quick pause. I want you to really think about this for a second. If we change the rules, say there are still 5 bead positions, but now we have 3 possible colors for each bead, why is the total number of combinations 3 to the power of 5 instead of 5 to the power of 3? It's a super common mix-up. The key is to look at it from the perspective of the bead itself. The position is fixed. It's the bead that is choosing from the 3 colors. Bead 1 has 3 choices and bead 2 has 3 choices and so on. So it's 3 multiplied by itself 5 times. Getting this combinatorics logic locked in your head is absolutely crucial for what comes next.
That brings us perfectly to section 2, the magic of rotation in finding patterns.
Check out these 2 monochrome necklaces we've drawn here. One is entirely red, the other is entirely blue. Let's call these the boring necklaces, or pile 2. What happens when you physically rotate that all-red necklace 1 bead over? Literally nothing changes. It looks exactly the same. If we have a number of colors, there are exactly a number of these monochrome necklaces. To find the really interesting patterns, we actually need to subtract these monochrome necklaces from our total pile. That leaves us with a total of a to the power of p minus a non-monochrome colorings. Notice how that perfectly matches the formula from Fermat's theorem? Pretty cool, right?
Now, let's zoom in really closely on this next drawing. Look at what happens when we physically rotate one of our non-monochrome necklaces. Let's say it has 3 blue beads and 2 red beads. If you rotate it clockwise by just 1 position, it looks like a brand new arrangement. Rotate it again, boom, another new arrangement. Because our necklace has 5 beads, rotating it gives us exactly 5 distinct-looking arrangements. They all belong together in one big rotation family.
So let's walk through the math steps logically using our example. Step 1. Our total pile of all possible red and blue 5-bead necklaces was 2 to the power of 5, which is 32. Step 2, we subtract our monochrome necklaces. There are 2 colors, so there are 2 monochrome necklaces, the all red and the all blue. 32 minus 2 leaves us with exactly 30 non-monochrome necklaces. Step 3, we literally just saw that every non-monochrome pattern forms a rotation family of exactly 5. So if we take our 30 remaining necklaces and group them by 5, we get exactly 6 complete families. 30 divided by 5 is 6. There's no remainder. The division works out perfectly.
Moving right along to section 3, why prime numbers matter, which is really the heart of the theorem.
Okay, here is where it gets absolutely crucial. We need to understand the difference between a prime number and a composite number in this physical space. Our prime number p was 5, and it gave us perfect rotation groups of 5. But what if we drew a necklace using a composite number, like 6 beads? Well, with 6 beads, you could build a necklace with a smaller repeating pattern, right? Like red, blue, red, blue, red, blue. If you rotate that specific necklace just 2 spots, it already looks identical to its starting position. It only creates a rotation family of 2, not 6. So those perfect groupings? Completely ruined.
And this is the fundamental mathematical reason why. A prime number, p, literally by definition, has no positive divisors except for 1 and itself. This means it is structurally impossible for a p-bead necklace to be built out of a smaller repeating cycle unless that cycle is just one single color, which remember is the monochrome necklace we already subtracted. Because p cannot be divided, every single non-monochrome rotation family is geometrically forced, to have exactly p unique rotations.
Which brings us to the ultimate aha moment. This is the proof, folks. Let's read through the logic together. The total number of color arrangements is a to the power of p. The number of monochrome arrangements is exactly a. Therefore, the remaining non-monochrome arrangements are exactly a to the power of p minus a. And because p is prime, these remaining arrangements fall perfectly into rotation families of exactly size p. Therefore, a to the power of p minus a absolutely must be perfectly divisible by p. We have literally just proven Fermat's little theorem, completely through the act of sorting imaginary necklaces.
Finally, let's wrap up with section 4, the beauty of primes and their hidden architecture.
I really want to share this powerful quote straight from our source material. Look more closely at prime numbers. They are small doors into some of the deepest beauty in mathematics. Think about it. We started with an equation that looked like pure, intimidating alphabet soup. But by understanding that prime numbers enforce a strict geometric structure, literally preventing smaller repeating patterns from existing, we found the hidden architecture underneath it all. Prime numbers aren't just random whole numbers that can't be factored. They are the fundamental building blocks that force the physical universe of mathematics to align perfectly.
To wrap up this explainer, I'm going to leave you with a thought exercise directly from our source material. Finish this sentence in your own head. Prime numbers are special in the necklace argument because... Really think about the exact structure we just visualized together. Think about those precise drawings we zoomed in on, and how the complete absence of smaller divisors locked every rotation into a perfect family of p. I really hope this visual metaphor has completely changed the way you view Fermat's little theorem and sparks your curiosity to explore just how deep the beauty of mathematics really goes. Thanks for joining me.